our Caltech astronomy stargazing lecture. We have a wonderful evening planned and great conditions outside, much better than the haze we've had the last few nights. So lots of transparency in the atmosphere and a lot of good targets in the night sky. I'm Dr. Cameron Hummels. I'll be your MC for tonight's event. And I'll have a few brief announcements and then we'll get started with the program. So this series of events takes place once a month on Friday nights. This is our final one of 2024, but we'll start up again in January. I forget the exact date, but I think it's going to be, our next one will be Friday, January 17th. And we're going to potentially hear all about accretion disks around black holes and the feeding of black holes and what goes on in the physics there. In addition to these events, we have a sister series of events that takes place in Old Town, Pasadena called Astronomy on Tap. Despite it being in a bar, it is all ages. Children and families can come, but it's at the Dog House Beer Garden in Old Town, Pasadena. That's on Green. And those events take place on Monday nights once a month. They feature two 15 to 20-minute presentations by local scientists, both those of us here at Caltech, but also scientists from Carnegie Observatories or the NASA Jet Propulsion Laboratory or UCLA, various different institutions around town. Our next one of those will be a week from this coming Monday on December 16th. There's a poster out front if you missed it, or you can check our social media accounts. This one will be specifically about the Chandra X-ray telescope. This is kind of a sibling telescope to the Hubble Space Telescope or to the James Webb Space Telescope. It's much like those. It's one of the NASA great observatories, but it operates in the X-ray part of the spectrum. So it studies what the X-ray sky looks like instead of what the visible sky looks like to our eyes. It's been in operation for 25 years. That's why we're having this event, because it's coming up on a milestone and still doing some amazing science. So we'll have two scientists who actively work with the Chandra X-ray telescope talking about the science that they do, looking at small active black holes and the regions around those black holes, as well as large clusters of galaxies, a variety of different phenomena that we can't see with our naked eye, but we can see with, or even with telescopes that operate in the visible part of the spectrum, but that you can see with a telescope like the Chandra X-ray telescope. So that, as I said, that'll be a week from this coming Monday. And those events also have telescopes and live music and astronomy themed pub trivia. They're a lot of fun and they're all free. So I encourage you to check that out if you're interested. In terms of other events, it's a little early, but if people are interested, we're helping to organize the Death Valley National Park Dark Sky Festival that will take place at Death Valley National Park, just a few hours drive to the northeast of here in the Mojave Desert. This will be a weekend featuring telescope, stargazing, but also a number of different lectures and presentations given by scientists, both from here at Caltech. We have a contingent going up, but also from NASA Jet Propulsion Laboratory, from some of the other NASA centers. And it's super fun. I've been helping out at this for the last 4 years, and it's like great every year. We'll be doing some of those astronomy on taps up there as well. And in fact, there are some cool planetary science geology talks that are presented where you walk among the different features in Death Valley, sometimes sand dunes, sometimes hillsides, because the surface features there really resemble some of the features that we find at other planets around the solar system. So it's really illustrative and interesting. That, I forget the exact date. I think it's February 21st through the 23rd. Somebody's bumping up against the lights. I think you in the back, yeah. No worries. These things happen. That's okay. It's okay. Little light show, little special effects. My special effects partner in the back here. So the Death Valley Dark Sky Festival will be you can look up Death Valley Dark Sky Festival online and find the exact dates, but I believe it's February 21st through the 23rd. And just to assuage any concerns, it's a really nice temperature in February. Lows of about 50 degrees and highs of like 75 degrees Fahrenheit. So it's really comfortable, not the 130 degrees that you might encounter in the middle of the summer there. Okay, so I think those are most of my announcements. For the rest of tonight, I'll introduce our speaker. He'll speak for roughly 30 minutes, all about galaxies and trying to simulate them on computers. And then we'll take a brief Q&A with all of you fine people, and then we'll have a brief intermission. And at that intermission, you have a choice. You can stick around and we'll have about an hour-long Q&A panel consisting of the speaker, myself, and two other astrophysicists from within the department to answer whatever questions you may have about astronomy or physics or space science. Simultaneous with that, we'll have telescopes. They're setting them up right now. They're on the fields directly behind us. So you can go back out the door that you entered through, go around the building, and then follow the signs. It's about, like a 30-second walk to get to the fields. And they've got 4 telescopes set up tonight to look at Saturn, Jupiter, the Andromeda Galaxy, probably the Orion Nebula, the Pleiades, lots of really cool stuff. So you're free to go back and forth between the telescopes and the Q&A panel, or just, hightail it out of here as you desire. But we'll be going until about 9:50, 9:45 or so. So feel free to stick around for as long as you want up to that point. Okay, so our speaker tonight is a very special speaker. He's a student who works in the research group that I do, and is doing some really amazing work in the field of astronomy and astrophysics. He was born in Jamaica and grew up in Jamaica before moving to New York as a young person, and then moved to, you grow up and you become a young person, right? So, and then moved to Iowa and went to school at University of Iowa, and did his undergraduate studies. He double majored, I guess almost triple majored, in astronomy, physics, and mathematics, before then coming here as a PhD student 5 years ago in the astronomy department here at Caltech. And he's been doing some really remarkable work in modeling the evolution of galaxies, doing full magnetohydrodynamic simulations of how the material moves around galaxies and is shaped by magnetic fields and shaped by cosmic rays, and a variety of other kind of exotic physics in trying to understand how galaxies form and how they evolve. So, and right now is his final year in his PhD program, and he'll be, everything goes right, he'll be getting his PhD in the next few months. So please welcome our speaker tonight, Sam Ponnada.
Hello, everyone, and thanks, Cameron, for the very generous introduction. So I'm happy to be here with you all today, and thanks for coming to my talk. So I'll be talking, like Cameron said, a little bit about how astronomers and astrophysicists like myself simulate some of the most beautiful structures in the universe on the world's biggest supercomputers. So if this works, it doesn't work, that's okay. That's working. So right now I'm showing you a fly through of a simulation of a very similar galaxy to the Milky Way. So what I want you to notice is all the very fine structure that exists in this simulation. So there's a lot of stars. They're sort of blue speckles. It's a little hard to see with the lights. There's dust that's obscuring the starlight, much like dust obscures the sun when we have a hazy day in Los Angeles. And there's tons of distributions of gas that's distributed in a very beautiful pattern of spirals throughout the galaxy in this very thin disk that characterizes Milky Way-like galaxies in the universe. But what actually is a galaxy? So galaxies are gravitationally bound collections of dark matter, stars, black holes, dust, and gas. And I'll break these things down in a little bit more detail. And specifically, I'll talk a little bit about the last part of magnetic fields and cosmic rays that Cameron described. But first, I want to kind of ground us in some observational or real day-to-day experiences of galaxies. So a couple years ago, I went on a hiking trip with my sister, and she was very patient with me as I stopped the car for 10 minutes because it was a really dark sky. And I wanted to take a photo of the sky with my phone because I knew there was something in the sky that night. So I want somebody to point out, if they can, where the galaxy is. There is a external galaxy to us, to the Milky Way in this image. And I want to see if somebody wants to be brave enough to point it out. Yeah. Right here? Yeah, that's absolutely right. So it's right there, and there's a purple circle around it now. So that is actually our nearest neighbor galaxy that's outside of our vicinity. It's called the Andromeda Galaxy. And the Andromeda Galaxy has been known about for many years. So it's actually the first written record of another galaxy was done by a Persian astronomer, Abdul Rahman al-Sufi. And in the Book of the Fixed Stars, he has this beautiful illustration of the Andromeda, who's depicted as a goddess with a large fish basically surrounding her. And it's uncanny that this same galaxy, which is here represented by these small dots that I've circled in purple, resides really close to the constellation Pisces, which is the fish constellation. And so this direct translation of what it was described as is, in English, the nebulous smear. And about 1,000 years later, we had the first actual picture of Andromeda taken through a telescope using a photographic plate. So this is the first actual picture of then what was known as the Great Nebula in Andromeda. We didn't really know what a galaxy was. At that point in time, the understanding of the universe was that the Milky Way was the universe. There were no other galaxies. The universe is just the Milky Way, and we're the only galaxy. So there's just this great big blob of gas in the sky, and people assumed it's just some blob of gas floating around the Milky Way. And this sort of makes sense because if you look at Andromeda on the sky through a telescope, the amount of space it takes up on the sky is comparatively large to other objects that are really close by, like the moon. So you might expect, oh, well, it's really big on the sky. That must mean it's really close to me. Or it could actually be a whole other galaxy out there, but that was kind of inconceivable to astronomers at the time. So this led to this whole thing called the Great Debate. And I just noticed this. Sorry, guys. If I can actually. It's okay. That's supposed to say the Great Debate in 1920. But this led to this whole debate about what the nature of the universe was and what the extent of the universe was. So there were two famous astronomers at the time who, trying to fix your thing. It is the California. Yeah. Do you guys want the lights dimmed more? Yes? Okay. Okay, this is a very interactive talk here. So, so there were two famous astronomers at the time, Curtis and Shapley, who were both arguing different conclusions. So one was arguing that actually this object was in our galaxy and the Milky Way is actually just gigantic. Whereas Curtis was arguing that this galaxy was actually another island universe, as they called them, and represented a whole other galaxy just like our own world, the Milky Way. In truth, I won't get into more detail about this specific debate. It's historical, and there's a really nice write-up of it online on BBC Sky at Night. But essentially, I'm not going to spend too much time on it because they were both wrong. And just a couple of years later, the world's largest telescope opened just a few miles away from us, Mount Wilson Observatory. And there was an astronomer named Edwin Hubble. Edwin Hubble sat at this telescope. Well, he didn't actually, he did sit at it, but he took pictures using it. And what he found was that he looked at Andromeda. And it turns out that Andromeda is definitely far away. And how he determined this is through noticing that one of these stars in this galaxy is a variable star. And it's a very specific kind of variable star whose variations in brightness are intrinsically tied to its period. And so we know exactly how bright intrinsically that object is. And so knowing exactly how bright it is and knowing that light falls as 1 over distance squared, we can get an exact measurement to the distance of that star. And now this is the same star that's been observed with the Hubble Space Telescope named after Hubble himself, following up on these observations almost a century later. And not only did he find that this was a whole other galaxy, when he looked through the 100-inch telescope on Mount Wilson and measured the distances to other galaxies using this method, he found that there's a ton of galaxies out there and the universe is extremely large. And so these galaxies that he measured, he noticed, most of them, basically everything that's not just really close to the Milky Way is moving away from us. And this led to a whole basically revelation in astronomy that, first of all, we're not the only galaxy. Second of all, there's many galaxies. And third of all, the universe is huge and expanding. And not only is it expanding, but it's doing so at an accelerating rate. So using different calibrations for measuring distance from our galaxy and building upon these other methods, for example, the most close objects to us, we measure through parallax. So right now, if you just take your hand and block one eye, I'm going to move in your field of view. And the angle by which I move can tell you directly about the distance to me because you know the distance between your two eyeballs, right? So that's the same concept. Since Earth rotates around the sun, if you measure the same object at two different points in Earth's orbit or during the year, you get an angular separation. And this angular separation is directly proportional through trigonometry to the distance to that object. And so through these other methods, like using variable stars, you can build a calibration for distances. And with things like supernovae, which some types of which have very intrinsic, well-known brightnesses, you can measure the distances to really far away objects. And then what they found when a group of astronomers in 1999 looked at these really far away objects, they found that not only are these objects all moving away from us, but they're also moving away at a different rate at different time periods in the universe. So the universe's expansion is not constant, but it's accelerating. And that led to the Nobel Prize in Physics in 2011. So you can get the idea that this discovery that Hubble made was very significant. So if we go to the present day, our understanding of galaxies has evolved a lot. Right now, we're looking at a composite image that's stitched together from the James Webb Space Telescope on the upper left and the Hubble Space Telescope on the bottom right. So what I want you to notice is that these images are sort of inverses. And that's because the different wavelengths of light tell us different properties of galaxies. So this is the electromagnetic spectrum. And we're all very familiar with the visible light, the rainbow. And that's a very narrow part of the entire electromagnetic spectrum. And I like to say that astronomers are archaeologists because every time we look into the universe, we're seeing things from the past. Light has a fixed travel time. And so the time it takes for the light to reach us has to have a finite distance as well. And so for example, the sun is 8 light minutes away. So every time the sun's rays hit your face, that was 8 minutes ago at the sun. So that same concept applies to galaxies, but we have to use light in different ways to infer different properties about galaxies. So the Hubble Space Telescope measures light around the UV to optical range of light. The James Webb Space Telescope, however, measures light more in the infrared regime. And these probe different characteristics of galaxies. So this is the Hubble Space Telescope image of the same galaxy. It's NGC 628. So you'll notice that there's a lot of blue, especially as you move further away from the center of the galaxy. And these are because young stars are really bright in blue and UV wavelengths. But you also notice that there's a lot of red, like especially red splotches that are interspersed between these dust lanes that you see. That's because the dust absorbs this really bright UV light from the young stars and then reprocesses it into redder infrared light. And so you're starting to see these dust-enshrouded star-forming regions associated with young star formation, so that when you look at the James Webb Space Telescope image, which is showing you the infrared, those things actually are the brightest objects. They're these dusty regions of the galaxy that are encircling these young stars. All this dust is reprocessing this UV blue light into infrared. And you can only see little patches of blue stars where the stars have had enough time to push away their surrounding dust and gas through radiation, through winds, etc. And so with James Webb, we're now peering into the earliest stages of galaxy formation. So since the universe is expanding, if you think about a cake that you're baking in the oven, if you put a bunch of raisins on the cake, the raisins are like the galaxies and the flour is like the universe. So if the cake starts to expand, all of the raisins are further and further away. And just like that, all of these galaxies that we're looking at in this expanding universe, their light, since light has a fixed travel time or travel speed, their wavelength gets shifted to redder and redder wavelengths. So some of these galaxies that you're seeing in this deep image of a cluster, on the left is from Hubble Space Telescope, on the right is from James Webb. You'll notice that there's several objects on the left that don't appear several objects on the right that don't appear in the left because they're very reddened, either because they're really further away from us, as in they're from the very early universe, or they're really dusty. So for example, if you look at this, try to find this in the left-hand image, you won't see it. There's plenty of other cases. So the James Webb Space Telescope is now really helping us understand galaxies at their very earliest stages of evolution. But part of the problem is that we can only see galaxies at snapshots in time. How do you connect all these different populations of galaxies at different times into the total ensemble of galaxies that we see at different times in the universe? What's the connection between all these populations, since we all live in one universe and there's some underlying physics? So in the modern cosmological paradigm, galaxies were born from overdensities in the very early universe. So this is basically a history of the universe from the Big Bang to present day. And please don't ask me about anything before like here, because that's purely theoretical physics territory. But Essentially, at the start, everything was a really hot mess. The gas in the universe was really hot and ionized, and there was a lot of light from the Big Bang that was really tightly coupled to this matter. But once the universe expanded enough that it cooled, eventually that ionized matter became neutral, like neutral atoms. And so when that happened, there was a distinct signal of light that was emitted from these electrons combining with protons to form neutral atoms. And we call this the cosmic microwave background, and that's going to be very important. But after that, these small overdensities that basically started as quantum fluctuations in the very, very early universe, I'm talking like 10 to the minus 32 seconds after the Big Bang, were basically blown up into these small overdensities that then through gravity started to pull in more and more matter to then form galaxies. And so this light that I mentioned that we see, the cosmic microwave background, which happened 380,000 years after the Big Bang, gives us the initial conditions basically for galaxy formation to simulate forward. So in this map of the cosmic microwave background, it's called a microwave background because it's at microwave frequencies. These little orange dots are overdensities of dark matter and gas, or regular, or baryons, which regular gas like regular atoms, hydrogen, helium mostly in the universe. This structure tells us about how much of the universe is composed of dark matter and how much is composed of regular matter. And the way that we know that dark matter, which I'll get to in a couple of slides, exists is because of the details of the structure of the fluctuations on this map. So essentially, if there were not another source of gravity beyond the baryonic matter that we see, the peaks of the oscillations in this map would look very different. And so it's one of the strongest indicators that dark matter exists in the universe, among many other tracers, which we can talk about in the Q&A as well. So if we take this idea of dark matter, of this collisionless fluid, this thing that doesn't have any pressure, that doesn't interact with light or any other force than gravity, as far as we know, we can really well reproduce the large scale structure of the universe. So this is a simulation called the Millennium Simulation. It was run in 2005 on, it was, I think at the time, the world's largest simulation of a cosmological simulation. But in any case, it's basically zooming in onto a galaxy cluster, showing you this really interesting web-like filamentary pattern that you might not have expected is what the universe looks like. And when we compare this to observations, which I'll show you on the next slide. So this is a map of the distribution of galaxies that we see in visible or optical UV wavelengths from the Sloan Digital Sky Survey. It also has this very web-like distribution. And so when we statistically compare this to what we expect from cold dark matter, which is the cosmological paradigm we operate under, it reproduces these statistics extremely well with very few parameters. But what about the details of all these little nodes in these webs, right? So these are the galaxies. The galaxies are forming at these overdense nodes in this web. And how do they actually form into the observed population that we see today? Since we can't see dark matter directly, the only tracer that we have is stuff that emits light, or galaxies containing their stars, et cetera. So as I mentioned before, galaxies are gravitationally bound collections of dark matter, gas, stars, dust, and black holes. So dark matter is a gravitationally interacting fluid that doesn't exert pressure on its surroundings. So it primarily only interacts through pulling things in. And as it pulls things in, it pulls in regular matter too, which interacts with gravity, just like you and me and Earth. So as this gas gets pulled in, it becomes gradually denser and denser. It falls towards the center of this really dense overdensity. And eventually you start forming stars out of this dense gas that cools and has the right conditions to be able to form stars. And eventually these stars interact with their environment. They have little tantrums. They have stellar winds. They blow up. They produce all these chemicals beyond hydrogen and helium, essentially. And eventually, some of them, when they die, they produce black holes. So what's crucial to understanding the observed distribution of galaxies isn't just the dark matter, which is sort of the infrastructure of building these cities of galaxies in the universe, but how these cities actually interact with their environment, right? So we have to understand how the galaxies, the stars, and their ecosystems are interacting in order to understand their observed properties. So how do we actually do this on a computer? So this is basically a to-do list if we're going to do this. So there's a big domain, the universe that you're trying to simulate, and we can start with just a small patch of it, but you have to kind of dice it up into little pieces. And then you have to have some initial condition. So the initial condition for our system is the cosmic microwave background. So we have a really nice map on the sky that tells us where we can start from and tells us the composition of the matter that we know has to physically interact. So then we have to write down all the gastrophysics that operates. So all the ways that the gas is interacting through gravity, through hydrodynamic forces, through energy and momentum being injected from stars, radiating into their surroundings, throwing stellar winds out, also going supernovae and injecting all sorts of enriched chemicals into the gas. And then you have to figure out the actual computational requirements necessary to accurately model these physics, because you want to make sure you're capturing how the gas is properly self-interacting and how the forces are, you have to ensure that the forces are well resolved. And then you run these simulations and you can compare them to these observations. Because as we know, the only things that we can see are not the dark matter, but the galaxies themselves. And so that's where FIRE comes in, and that's the collaboration that Cameron and I are a part of. Stands for Feedback in Realistic Environments. And so we can take these sets of self-consistent equations, discretize them into little chunks that represent some small portion of the universe around, say, a galaxy or a small group of galaxies, and then run them on the world's largest supercomputers. So the one that we use very often is called Frontera. It used to be the 14th fastest supercomputer in the world, like 5 years ago, but now it's the 52nd. So that goes to show how much computing has also gone forward in just the past 5 years. And this is an NSF-funded machine. It's actually the largest academic supercomputer in the US. And if we were trying to run these simulations at these really high resolution required to capture all this physics self-consistently, on my laptop, it would take 200 years. And I don't know about you guys, but I'm not going to be around for 200 years. So on these publicly funded machines, it takes 20 days, which is really incredible, given the advances in computing and the advances that we've made in numerical techniques to simulate these sorts of physics. And so here's what this looks like. So on the left, I'm showing you an example of a FIRE simulation of a Milky Way-like galaxy, actually the same one I showed you on the first slide. And on the right, I'm showing you what it looks like in starlight. So on the left, we're evolving all of the dark matter interacting gravitationally within the environment of the galaxy. So it's having all these mergers of smaller galaxies. It's blowing out gas from stars forming, going supernovae, and also explicitly just resolving all the chemical physics of the gas. So the stars enrich their surroundings through supernovae. The gas is allowed to cool through radiative processes. And this is all captured self-consistently to then produce these very realistic galaxies. And I'm going to give it a second because it's going to start looking like the Milky Way pretty soon. I think this is the longest movie. So you can see all sorts of different physics interacting. So you can see in this left-hand panel, I'm showing the different temperatures of the gas. So not only is it resolving the evolution of this galaxy in its context, but also all of the different phases or temperatures of gas that are required. So on Earth, we're used to room temperature and like maybe plus or minus 100 degrees, right? If you go to the extremes of the South or North Pole. However, in galactic systems, the temperature range that we need to think about spans 10 orders of magnitude. So in our simulations, we have to follow the cooling of gas all the way from 1 degree Kelvin to 10 to the 10 or 10 billion degrees Kelvin. And I'm going to show another example of how these simulations can be useful. So this is another fly through, like I showed on the first slide. But this is of a Milky Way-like galaxy that goes through a merger at late times. So galaxies interact, and these mergers can be very important for how galaxies evolve and form into different properties. So this galaxy happens to have a companion, much like the Large Magellanic Cloud, which we see in the night sky in the southern hemisphere, that merges with the galaxy at this late time and results in different processes that have been studied in some of the papers. But the idea here is that with simulations that can resolve the context of a galaxy rather than just resolving a single galaxy itself, we can start to understand how different processes like galaxy mergers and interactions play a role in forming the different population that we see. And this is one last example of a movie. So I mentioned Andromeda earlier. The Milky Way and Andromeda are called the local group. And so this is a direct simulation of a local group-like system that has a Milky Way-like galaxy at present day, as well as an Andromeda-like galaxy. And so you can see how the large-scale structure eventually gives rise to this local group-like system. And this sort of direct comparison has been used to test different problems with cold dark matter that have been proposed. So for example, it was long thought that this cold dark matter paradigm produces too many satellite galaxies around the Milky Way. However, when we looked at these simulations with the full feedback physics involved, we noticed that even if you have a lot of these dark matter halos, because of the gravitational interactions in these group systems, you can actually resolve this so-called missing satellites problem just by having these gravitational interactions between massive systems, as well as the feedback from stars, basically destroying a lot of these really small satellite galaxies that are otherwise predicted to be seen. So I touched a little bit about some of the broad things that we can learn from these types of simulations, but in the last couple of minutes, I'm going to hone in on a couple of topics that are closer to my research. So I've sort of glossed over it, but galaxies that are filled with gas are also filled with magnetic fields that are glued to this gas. And these magnetic fields are like the railroads on which charged particles that move at high speeds, we call them cosmic rays. They move close to the speed of light. They travel along these magnetic field lines along helical paths. And so on the left here, I'm showing a map of the magnetic field geometry in our galaxy as observed through the Planck instrument. So the tricky thing with magnetic fields and cosmic rays is that we can't directly measure either of these components. And I'll get to this in the next slide. But the ways that we measure these components are often very, very indirect and involve a lot of assumptions. And so one of these indirect methods that we use are sort of like cosmic sunglasses. So we live in SoCal, everyone wears sunglasses, but the idea behind sunglasses is that they are polarized and they block out certain polarizations of light so that you have less glare, right? So the same sort of thing happens in interstellar space where these little dust grains are sort of like little tops and they have basically a long axis and a short axis. And the magnetic field wants to align these little tops such that the short axis is parallel to the grains. And so when you see a star that is emitting all this unpolarized light, much like the sun, you have this screen of cosmic sunglasses in between you and the star that then tells you about the direction of the magnetic field. And so that's the basis for how these sorts of magnetic field line images are made. And there's also cosmic rays. And so actually recently, everyone's become very familiar with cosmic rays because there's been all this aurora happening all over the year. But essentially, stars like the sun emit winds. These winds are filled with charged particles that then follow magnetic field lines. And as we know, Earth has a magnetic field. And so once these charged particles get to Earth, they spiral along the magnetic field lines. And since Earth has a polar magnetic field, they primarily hit the Earth's atmosphere along the poles. And this is what causes the aurora. But not only are these cosmic rays floating from the sun to the Earth, but they're emitted all over the galaxy from stellar winds and from supernovae when stars eventually die and inject their energy into the surroundings. And as these cosmic rays whirl along these magnetic field lines, they emit a type of radiation that we call synchrotron radiation. And so the problem with these two components of galaxies that we know exist but want to better understand is that we've only directly measured magnetic fields and cosmic rays in our local neighborhood. So the Voyager satellites were released or launched into space in 1977. And just a couple of years ago, I think when I was in college, they were claimed to have passed out of the sun's heliopause into interstellar space. And so the measurements that were taken from the instruments on Voyager could directly measure things like the magnetic field strength and the amount of cosmic rays in interstellar space. However, that's only in our local neighborhood. And as I've sort of alluded to, galaxies' properties and how they interact with their surroundings are tightly coupled. So this is an artist's conception of a galactic ecosystem, and you can see the disk and all the stars forming there. But there's also all this material that's filling these dark matter halos around galaxies. It's gas that's being accreted through gravity from larger scales into the galaxy. And it's also gas that's being expelled out of the galaxy through stellar activity or black holes that then interacts with the surrounding gas to then influence how these galaxies actually accrete the fresh fuel for star formation. And what's been realized in recent years through numerical and simulation advances, this is a movie that Cameron made from some of our simulations, is that when you actually include cosmic rays, these can very drastically change the properties of these galactic ecosystems. So on the top panel, I'm showing a movie of the same simulation, same guy from the first slide, without cosmic rays. And on the bottom is all the same physics, but with cosmic rays. And so what I want you to notice is that in the movie without cosmic rays, and I'll play it again, the outflow structure from the galaxy is much more chaotic, and that results in the phase or the temperature structure of the surrounding gas in being much warmer. And that's also reflected in this plot, which is showing the temperature as you go further out from the center of the galaxy. Whereas in the simulation with cosmic rays, for all the same other physics included in the same galaxy, the outflows from the galaxy are much more stable. And the cosmic rays can establish these really extended halos that then support the gas and result in a cooler structure of the gas. And what's been interesting in recent years is that some of the latest observations from Hubble Space Telescope and other observations that probe these halos find that there might be in better agreement with what we see from these types of simulations than the simulations that haven't been able to model them just out of computational or theoretical complexity. But the problem is that we actually have no idea if they actually get out of the galaxy's disk into their surroundings and establish these really large scale pressure gradients that can affect these temperature properties and so on, because the only direct measurements we have are right here, like in the local interstellar medium, just outside of the one little star, the sun, in like 24,000 light years away from the center of the galaxy. And so we don't actually know what drives these cosmic rays to move or how they move outside of the local environment, because these cosmic rays are traveling along these magnetic field lines, but the magnetic field lines can be really tangled, and they're tangled on these really small scales that we can't directly simulate or observe, and that's what actually sends these cosmic rays throughout space. But with the newest generation of simulations, we can start to understand these physics a bit better. And so we can directly simulate this synchrotron emission, or this emission that comes from these cosmic rays gyrating around magnetic field lines, and compare them to observations to, one, understand the things that we're seeing and estimating through these indirect observations and assumptions, and two, see if we can put in different prescriptions for the physics from pen and paper calculations for how these cosmic rays bounce off of these twists and turns in the fields to see if they will show up in different frequencies or wavelengths. And here, particularly looking at radio frequency observations of galaxies. And not only that, but we can start to connect all the different pieces or different wavelengths that we observe galaxies in across the electromagnetic spectrum self-consistently. So whereas before a lot of simulations would only primarily be able to connect the far infrared emission or the UV optical emission that's associated with stars and dust to observations, now we can extend this even further out to radio frequencies and also gamma ray frequencies, which would be even further over there, and try to understand how the different properties of galaxies emerge from these physics that otherwise might not be immediately clear. So we can start to understand, for example, there's this longstanding correlation between the far infrared emission and the radio synchrotron emission of galaxies, but these arise from very different processes. This arises from dust, this arises from cosmic rays, but using simulations with modern techniques, we can start to understand how these different properties emerge and how they're connected in really great detail. And so I'll stop there, but in summary, galaxies are gravitationally bound collections of dark matter, stars, black holes, dust, and gas. Cosmic rays and magnetic fields are very important potentially, but we basically have no idea whether the cosmic rays get into the surroundings of galaxies efficiently. And while we can really well reproduce the really large scale distribution of galaxies, we're still trying to figure out how to reproduce the very detailed observational constraints of their populations that we see in the universe across different periods of time. And right now, simulations are starting to expand this observational parameter space to be very powerful test beds of particularly the physics of magnetic fields and cosmic rays, but also for generally understanding the physical processes which influence galaxy formation over cosmological time. And with that, thank you. All right, any questions from the audience?
Okay, hold on.
Nice talk, Sex. Can we use the current observation and the initial and reverse simulation to get the idea of the beginning of the universe?
Sorry, could you repeat that question? And hold the mic a little closer, please.
Oh, sorry. Can we use the current observation and the initial and the reverse simulations to get the idea of the beginning of the universe?
I see. So yes. So essentially, that's part of what So this is basically observational data that represents the distribution of galaxies through the universe. And so this gives us a very detailed prediction for what any sort of model for the evolution of the universe has to produce at present day, right? So these sorts of large scale survey constraints are what we use in order to verify different models for how the universe expanded and evolved over time.
And can the current state of the universe be reversed in the simulations to go back in time to try and reproduce this?
Yes. So these, so for example, these movies that I've shown, this one might be better. So this simulation is essentially reproducing the things that we see at present day. So we can get an understanding for how things led to that state just by looking at the evolution from our initial condition. So if you play this movie in reverse, basically, it tells you the same information.
Additional questions?
Oh, yes, I wanted to ask, in the research article Hooke's Lines and Sinkers, you are exploring what can affect the far infrared correlation. And so far as I understand, there is like an unexplored territory how active galactic nuclei is affecting the far infrared correlation. As far as I read into it, you're saying that the black hole accretion should be the significant component in that influence. Are there any other significant components? The thing is, I would like to understand better the nuclei interaction with the galaxy.
So the question is about basically active galactic nuclei are black holes at the centers of galaxies, which I didn't touch on in this talk, but they're an important source of feedback in galaxies and how things evolve and interact. So black holes at the centers of galaxies can also be very important sources of cosmic rays. And this plays a role in how these observed properties might play a role. But for the specific details, if you want to chat after as well, we can do that.
Good question, but very high level.
Yeah.
So my question is, what are cosmic rays, and are they interacting with gravity? Are they interacting with galaxies through electromagnetism?
That's a good question. So cosmic rays are charged particles like regular protons and electrons that are accelerated to really high speeds close to the speed of light. And so these, because they're charged, they feel a magnetic force along the magnetic field lines. So they're tightly coupled to the field lines that are throughout the galaxy. And so they do interact with the galaxy through radiation, but they also interact through pressure. So even though there's not that many cosmic rays, there's about one regular atom for every million or billion cosmic rays in the universe. They're so energetic that since they interact with the gas and they're glued to the gas, they actually push the gas. So the primary effects that we see in the simulations come from their effects of pushing on the gas rather than them interacting through the radiation they're emitting, because this radiation that they're emitting is pretty low energy. Their primary effect is through actually directly pushing the gas.
That pushing is through the electromagnetic force. Like when you get two magnets too close to each other and one can repel the other or draw the other one back, it's the same kind of effect. More questions? Yeah.
Hi, it was really good. As you can see the past of the galaxy, you can see the future of the galaxy, like how this gas is concentrating in one point. Like you can see in the future, there's a star and there's going to be planets, or that's like not in the simulation?
That's a good question. So you can evolve these further in time. So for example, one case is Andromeda and the Milky Way. So Andromeda is moving towards us. And in about 3 billion years, given its current trajectory, it's going to merge with the Milky Way. And so that's something that we can directly simulate through simulations. In terms of stars and planets, those are way too small for us to directly simulate in these sorts of simulations. So the smallest scales that we're resolving in these simulations are something like 10,000 times the size of our solar system. So if we wanted to directly simulate star and planet formation in this simulation, it would require a lot more computational power. But what we've started to do is we can take the same base physics of gravity, radiation, hydrodynamics, and we can zoom in on individual patches of a galaxy simulation like this down to the scales of individual stars and individual clouds that form stars. And so there's a whole other collaboration that started from another PhD candidate. He used to be a student here. He's now a research scientist at the Flatiron Institute. It's called StarForge collaboration. So they actually directly simulate the formation of stars and planets from the same base physics that undergirds all of this structure formation in the universe. And so we have some simulations now that are actually zooming down from these cosmological, really large scales down to these really, really small scales on the level of planets.
We can take one more question before we have our intermission here.
Hi, Sam. In your simulation, the one that showed the temperature of the galaxy, it was cold in the middle, and I would think it would be hot in the middle. Why was it cold in the middle?
Yeah, it's a good question. So I'm trying to find. Good movie for that. Yeah, so gas cools via different radiative processes. So denser gas, especially gas that gets enriched by metals from stellar activity like stellar winds and supernovae, is very metal enriched. And so these metals can actually cool the gas very efficiently through emitting light. So they take energy away from the gas. And so even if there's little bursts of energy, like you can see these little blips of hot gas basically being expelled out of the galaxy from the star formation and supernovae, this gas quickly cools down. So on the timescales that you're looking at in this video here, you can't really see the hot gas that exists in the galactic disk, but there is a lot of hot gas there. Actually, that fills most of the volume of the disk. But given the movie's contrast and the timescales over which the movie was made, you don't see the actual hot gas that can be pretty transient. The gas in this, so a lot of the gas is at something like a few hundred Kelvin. So actually room temp, yeah, like kind of close to room temperature. But the gas that fills most of this volume is something at like 1,000,000 Kelvin. So the contrast is very high.
Okay, let's thank our speaker again. So again, we're going to have like a 5-minute intermission. We've got the telescope set up outside. You guys are welcome to go check out Saturn, Jupiter, the Andromeda galaxy, like we heard during the talk. We're going to get our Q&A panel started here in about 5 minutes. You're free to go back and forth between the two. Otherwise, if you head out, our next event is middle of January here, and our next Astronomy on Tap is a week from Monday, December 16th at the Doghouse in Old Town, Pasadena. Thanks for coming, and we'll start our Q&A panel in just a few moments. Thank you. That looks amazing. Better than it's ever looked before. Amazing. Okay. Welcome back, everyone. Thanks for sticking around. We're going to start our Q&A panel where we first we'll go through, do a brief introduction for each of us about what sort of science we work on. We'll take questions on any topic, but just so you know what we're most knowledgeable on the topics of, and then we'll start taking questions from both you as well as our online YouTube audience that's watching this remotely. So as I mentioned, I'm Dr. Cameron Hummels. I do a lot of research, much like what Sam talked about in his presentation, trying to model the evolution of galaxies, specifically the atmospheres around galaxies and the environments around galaxies, and then try to convert those simulations into what we think our telescopes would be able to see, both from visible wavelengths of light, ultraviolet wavelengths of light, and so on and so forth.
Hi, my name is Isabel Sands. I'm a PhD candidate here in physics. I work in the same group as Cameron and Sam, but on slightly different things. I focus on astrophysical probes of dark matter, and I run simulations of galaxies forming with different models of dark matter. We don't know what dark matter is, so that gives us a lot of room to kind of play around and test different theories.
Hi, my name is Jacob Faber. I'm a third-year grad student, outsider in the group. I'm not in their research group. A little variance. I work mainly in radio astronomy, so in the radio wavelength portion of the electromagnetic spectrum, mostly on neutron stars, looking at neutron stars, a little bit of black holes, and generally speaking, a lot of sort of wave optics phenomenon. So the way that light moves through and interacts with interstellar plasmas in galaxies, the circumgalactic medium, and just right up next to the source. Yeah, that's about it.
You already heard from me, so.
Okay. We can take questions from all of you. Do you guys have any questions about astronomy? You were first. I'll get you next.
Thank you so much. So the great poet William Blake, wrote, "To see a world in a grain of sand and heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour," right? In one of his most famous poems. And when you get to this level of astronomy, it becomes kind of poetic. And the idea behind these lines of poetry is simply, I would say, in modern terms, something fractal. Right, because in fractal things, a small thing has elements of the big thing that it constitutes, and vice versa, right? Like so, if you see this one paisley sign, there's like infinitely small paisleys within that big paisley, right? So eternity can be seen in an hour, or somehow a human being can even reflect the entire universe in some way, right? So, in your research, Sam, did you notice anything fractal?
Thanks for the detailed question. Yeah, there's a lot of fractal things about astronomy, especially structure formation. So, as I showed, there's this sort of spider web-like pattern of the distribution of galaxies and dark matter in the universe. And a lot of things in astronomy follow power law distributions, which are fractal or self-similar by nature. So you keep zooming in, and it still has elements of the same structure. So because of gravity goes as 1 over r squared. That gives you a lot of fractal things, like the way that galaxies form is very similar in some ways to the way that stars form, with like gravitational collapse. And so I guess a lot of it is fractal.
There have been some papers that have looked into this explicitly to look at what is the fractal dimensionality of different phenomena in the universe. It's not fully self-replicating on all scales, or else we'd have stars that weren't just the size of the sun, but are 1 million solar masses or 1 billion solar masses. And it's not that, but there are a lot of, as you suggest, and as Sam's alluded to, there are a lot of kind of self-similar structures on various different scales. The one that comes to mind for me is when you look at a galaxy, a spiral galaxy like our own Milky Way, it has a nice disk, kind of rotating disk feature. But you see that same sort of scale, that disk structure for protostellar stars as they're in their formation, or accretion disks around black holes, or Saturn's rings around Saturn. And that's really a function of gravity and angular momentum, the conservation of angular momentum, preventing those things from collapsing into a point, but being kind of conserved in a disk structure. But no, that's a very insightful question. And it is something that pure mathematicians have tried to look at for this self-similarity, fractal behavior of the universe. It's not perfectly so, but there are features of it.
Yeah, just to build on that briefly, I think this is there's a lot of analogies sort of in ways of modeling particles and light, sort of in different sort of regimes of modeling. For instance, the way that light travels through a medium, you can think of it as a ray, or you can think of it as like a fully complex wave that involves like phase, for instance. But way back in the day, this cosmologist Jim Peebles, wrote in his book The Large Scale Structure of the Universe. He had a chapter on how you can effectively model sort of the cosmic web, or cosmic skeleton, as it's called sometimes, as basically light traveling through a medium, instead of sort of an analogy to particles traveling through a gravitational field. And there's really beautiful sort of similarities. Again, they're not perfect, but for instance, when you see sort of light refracted through sort of a pool, the surface waves on a pool, and you see sort of the pattern on the pool bottom, that pattern is strikingly similar to sort of the distribution of galaxies that make up the cosmic web. And so that goes to show sort of the kind of the beauty in the presence of power laws in the universe and physics in general. And this sort of ties into turbulence as well. A lot of sort of consistent turbulence cascades that exist in our atmosphere, in the interstellar media of galaxies, all the way from the smallest structures to the largest structures. Yeah, so the role of fractals is a really beautiful way to sort of connect, sort of create kind of a picture of universal phenomena, sort of universal across vast scales that span many orders of magnitude.
Good question. Yeah.
Hi, friends. I have a question, which is why, okay, I hope I put it correctly, but so it seems like you guys study astro at different like EM spectrums. And I'm interested as a like astrophysicist or scientist, why do you choose specific spectrum you're interested to study? What sort of questions you gain per that specific wavelength, and like, whether that fits into like sort of like your philosophy as an astrophysicist, or like the personality or sort of approach you like to take in doing your physics?
Yeah, so I can answer sort of my approach to this, because I have a very strong motivation for choosing to look at any specific part of the electromagnetic spectrum, which is I'm looking for specific signals of dark matter. I'm always more interested in figuring out something about the underlying nature of dark matter than I am about the like astrophysical observable itself. And that's kind of just sort of a reflection of my background coming more from the physics side than the astronomy side. So for instance, I right now have projects that look at radio observations of galaxies, rotation curves, which can indirectly measure the amount of dark matter in a galaxy. But I also have a project that's modeling gamma ray emission from cosmic rays, which is the whole entire other side of the electromagnetic spectrum. And I'm looking at that because it's been suggested that there's a gamma ray signal from the galactic center that could come from annihilating dark matter particles. So that's how I pick.
Yeah, so I have pretty much stuck to radio waves throughout sort of when I started doing astronomy up until now. I mean, there's a variety of reasons, but radio waves are really interesting if you're looking at some of the most compact objects in the universe, things like black holes and neutron stars, sort of dead stars that have collapsed to form either, like a ball of neutrons, or all the way down to, form a singularity, a black hole. but they also so they're reflective of really extreme environments, and can tell us a lot about them, and sort of even the things that we like, for instance, how neutron stars emit radio waves, which, you know, for a certain type of neutron star in our galaxy is called a pulsar, which is effectively like this interstellar lighthouse that has two beams on either of its poles and rotates really, really rapidly. We don't really understand how that emission happens, but we can still use those radio waves to probe things that the radio waves interact with. So when they pass through like the interstellar medium, they undergo electromagnetic interactions with free electrons, for instance, that tell us like how much stuff is in between us and the star. And we can actually use that to sort of map out the distribution of matter along that line of sight all the way to the source, all the way to the star. So it's kind of it reflects really extreme environments, but it's also a really excellent probe that can basically serve as this flashlight for sort of all of the matter that lies in front of it. So I mean, radio waves, you know, radio astronomy spans a much broader range than that. But for me personally, I think that's where the motivation comes from.
Yeah, I think sort of more high level. Anecdotally, I feel like different personalities work in different wavelengths, at least for the observational astrophysicists. But I think working on the theoretical or computational side, you kind of forced to be more wavelength agnostic, because there's so many. Because then the different parts of the electromagnetic spectrum represent different constraints of the same physics, right? So if you're trying to reproduce like a realistic galaxy, for example, if it looks right in stars, but then looks like crap in radio or something, then do you really have a good model of the galaxy? So that's sort of why, as I've tried to show, like I've sort of been wavelength agnostic and simulating across the electromagnetic spectrum, but they are sensitive to different processes, and there's unique things about each one. For example, radio observations, we can, if light is getting redshifted as the universe expands, we can see further at redder wavelengths because of the redshifting of light. And so there's information that we get from different wavelengths about different times in the universe. There's information that we get about different processes. For example, gamma rays tell us about cosmic rays too, because cosmic rays smash into regular matter, and then they create particle accelerators like the Large Hadron Collider that then produce gamma rays. And so these different wavelengths of light tell us about really different processes that are all interacting in the same galaxy. Yeah.
The only thing I'll add, I echo the statements of my colleagues here. The only thing I'll add is, for a long time, we were really constrained as scientists to only being able to view things through what we ourselves could see, visible light, and the optical parts of the electromagnetic spectrum, which is just a tiny fraction of the entire electromagnetic spectrum. And the analogy I always think of is playing the piano. Like if you hear someone playing the piano, they're going across many different octaves, but by limiting yourself just to understanding and seeing stuff that you could see with your eyes, you're limiting yourself to like 5 keys on the full range of a piano. And so there's so much more that's going on. If you were only hearing those 5 keys worth when someone's playing a concerto or something, you'd really be missing out on a lot. So really the goal, again, echoing what Sam was just saying here at the end, is trying to make as many predictions from the simulations as possible across many of these different wavelengths of light across the entire spectrum, and then trying to match that with the various different observations to make sure we really understand the entire phenomena instead of just one small segmented part.
I'll add just one last thing, like Cameron was saying, like we are restricted to optical, and our atmosphere allows optical light in, but like we have an ozone layer, right? And that blocks a lot of UV light at most UV wavelengths. So the UV observations that we can only get if we send something into space. And so some of these wavelengths of light were just previously basically limited by our constraints as humans on Earth. Like we can't have to look through the atmosphere when we're looking from Earth. And so that blocks out a lot of different wavelengths of light, for example, UV, for example, X-rays, for example, some bands of infrared light that water molecules from water vapor in the atmosphere absorb. And so we're kind of blind to those wavelengths of light. And now with space technology, we're able to actually see these things.
But there are still some wavelengths that we still can't perceive. The longest wavelengths in the radio part of the spectrum are blocked by the ionosphere in our atmosphere, and we still haven't actually been able to do any observations longward of, what's the wavelength range for kilohertz. Yeah. So there's still like unknown, undiscovered country out there that we've never been able to see with the instruments that we have on within our Earth's domain. So it's exciting. There's still cool stuff out there to discover. Additional questions?
I would like to ask about one particular topic that I'm very passionate about, and that's science communication. And I would like to understand which part of your research do you find most difficult or challenging to explain? And it doesn't have to be just to public, but maybe to other researchers as well.
Asking us to explain the stuff that's hard to explain. Okay. Well, so the thing that jumps to mind most recently, there was a major discovery that was made about a year ago involving something known as pulsar timing arrays. And we had an event here at Caltech hosting some of the scientists who had been involved in this research. And the announcement was made last June. So if you go onto our YouTube channel, you can find the lecture. But essentially the idea is that, because it's layered trying to explain this, because you have to explain what a pulsar is. A pulsar is a neutron star that's a bit like our star, except it's usually more dense, or it's usually more massive. It's far, far more dense. In fact, it's so dense that, like, what is it? A teaspoon of that material would weigh as much as Mount Everest would weigh here. It's incredibly dense material. And we actually don't understand the internal dynamics of how that material exists, because we don't have any just lying in your cupboard or whatever. So you have to talk about neutron stars, why they generate massive magnetic fields that are millions or billions of times more strong than our Earth's magnetic field here. And then you have to talk about how we can probe these pulses that come from these, from several different ones simultaneously. And that tells you something about the warping of space-time between us that's caused by gravitational waves that are traveling through that. It's a mess, and it's complicated, and it's really hard, but there was a very important result that was made in this recently that's going to be able to reveal things like the presence of supermassive black holes that are merging in the distant universe that we can see not through our eyes or our ears or any electromagnetic waves, but through gravitational waves that are traveling through that. And so stay tuned. I'm sure there will be more results in this field in the next few years, because there's a number of new instruments that are coming online and continuing to operate that are able to do this measurement more effectively and more precisely over time. But it's certainly an incredibly difficult thing to distill down to something that people have an intuition for, much more so than stars or galaxies or planets or that sort of thing.
Yeah, I was going to say the exact same thing. I think that topic is a really interesting sort of exercise in science communication, because I mean that was the first like pulsar timing arrays, my entry into research when I was like 18, and I sort of saw this evolution in the field of trying to explain this to the public as we were getting closer to having a result, which in this case was basically the noise of all of the mergers of supermassive black holes that have happened throughout the entire universe that make up this like background sort of cacophony of not sound, but in this case gravitational waves, signal. For instance, the first public talk I heard about this said exactly what I said a few minutes ago, which is they compared pulsars to lighthouses. And you can kind of sort of instantly sort of see imagine what that would look like, where you kind of have a ball that, as Cameron said, is like extraordinarily dense with these two beams that are on opposite sides on the poles, that's rotating at roughly like, once every millisecond, once every 100 milliseconds or so. And then you think of that, okay, as like a flashlight, and then you have to explain gravitational waves. And so there's, people kind of construct little visuals of like a box that's moving in both directions to indicate sort of a quadrupolar motion that gives you a sense of what people say when they talk about like ripples through space-time, and expansion and contraction of space-time due to this motion. But gravitational fields are such sort of they're so esoteric, they're really hard to intuit. But there's a lot of like, I mean, I've heard people talk about gravitational waves in the context of like Jello. Like there's still like points where you can kind of access the visual of what you would need to grasp it, at least at a high level. Yeah, so constructing those analogies, I think, is incredibly useful, even for such a challenging thing to sort of wrap your head around, even if you've been in the field for a decade.
I have an answer to challenges about communicating my research to other researchers. It can be very challenging to communicate with someone who's in a different field as you, or kind of across fields if you're on the boundary of two of them, which I kind of am. I characterize my research as astroparticle physics. So I have to justify everything to the astrophysics community and the particle physics community. And well, for one thing, at Caltech, this is the astronomy building. I work here. The particle physics building is across the street. And now with like all of the construction, it's actually somewhat difficult to get there. So there's already like a physical barrier, but also like just researchers in both camps kind of have very different ways of thinking about things. Their priorities are different. So for instance, I can talk about the same paper to both my research group in this building and the research group across the street that does particle physics. And I have to tailor my talk sort of to their interests. The particle physicists don't want all of the gory details. Most of the astrophysicists in this building don't necessarily need to know all of the details of where like a given dark matter model came from.
I'll get to you, but I want to see if there are any first timer questions tonight before I start the repeats.
So like when you're modeling theoretical galaxy, and then is it like when you're comparing it to like observational galaxy, is it more exciting to see like, oh, this is what I thought it was going to be, and this is like what I got it right, or is it more exciting like, oh, this is so different from what I thought it was going to be modeled? Like the universe is behave very differently than what I model. What are your thoughts?
Are we more excited when we get things right or when we get them wrong? I don't know. It's a mix, I'd say, right? Like, obviously, it's nice to do something and be like, oh, I did it right. I didn't like have a bug in my code. But I think it's more interesting to find something new, as long as you're sure that it's not just you made a mistake in your calculations, right? If you see something that's different between your predictions and reality, the first guess is that you made a mistake somewhere along what you were doing. But if you can rule out all of the mistakes such that you're making an authentic prediction that is differs from what we expect when we look up in the night sky, that's truly remarkable. That's very exciting, I think. And so I think scientists in general are very driven by being the person or the team that gets to discover something new that no one knew about before, or that there's a mistake in Einstein's theory of relativity, or some calculation that was done by someone many years ago, or in quantum mechanics, some new effect that we didn't account for. As long as you just didn't make some, forgot to add a divide by 2 or something like that in your own calculations. That's what I'd say. But do you guys want to add?
Yeah, I would say the same thing. Like, I think the most exciting time is when there is a contradiction between the observations and the theory, because that means that there's probably something or possibly something new to find out. And so that's like sort of purposefully like how I chose my research topic, because we like sort of know what's going on in the galaxy, but don't really know what's going on outside of the galaxy. So we have these models that predict the like observational properties of the galaxy itself really well, like how many stars they form, how big they are, their colors, etc. But when we look at indirect observations of the gas around galaxies, we basically have no model that very well predicts what's going on out there. And that's really crucial to understanding how these systems form and evolve. So that contradiction is sort of what drives this whole area of research, of trying to compare these simulations to observations in the right way. Because that either means maybe there's something wrong with the interpretation of the observations because we're seeing everything on 2D in the sky, right? But in the simulation, you have all the information, so you know everything in 3D. But then that also means you have to compare these things in the right way. If you just take a value from a simulation and then take a value that you inferred from measuring something that's not directly measuring that value, you could be just wrong because your assumptions are wrong. Or it could mean you checked everything, all the assumptions seem to hold, but then there's some physics that you're missing. And so that's sort of what I think is very exciting.
Question in the back. And as I go to get to this questionnaire, if you want to look through the telescopes, I encourage you to do it now. They'll probably close them down in about 15 minutes. So if you want to check them out, we'll still be going in 15 minutes here, but I just don't want people to miss out on their opportunities to look through the telescopes because they're pretty sweet.
Hi, this is for Sam. In one of your slides, I think it's the slide where you talk about all the steps that go into creating the simulation. You mentioned something called gastrophysics. What's gastrophysics? It sounds like cooking to me.
Yeah, that's just a pun. Yeah, so yeah, you know, gastrophysics is in the physics pertaining to all the gas that's in the galaxies. But yeah.
Yeah, because oftentimes when we're dealing with the interaction of stars, stars for the most part can be described as Sam said, as a collisionless fluid. So it's kind of like a fluid, but where the particles don't run into each other because their sizes are small enough relative to the distances that separate them that they don't actually have collisions. The same is true for how we model dark matter, like what Isabel does. Most of the time. But when you start dealing with gas, you know how fluids interact like liquids. If they run into each other, they certainly do encounter each other. And then the fluid dynamics that you get from those interactions is very complicated and difficult to model. So it's kind of jokingly referenced as gastrophysics as its own business because it's hard. Because fluid dynamics is hard. Any other questions from audience members? Yeah.
Great talk. I was wondering how much diversity is there in terms of like how galaxies are formed and how they sort of exist in space? And is there any sort of like regional rule in the sense that galaxies closer to our own are more similar to ours, and as you move farther away, they start to change? Yeah.
That's a great question. So I sort of alluded to it in one of the slides where I showed the really deep image of taken from James Webb and from Hubble, but there's a very strong like bimodality in the distribution of galaxies. So there's galaxies that are really blue and there's galaxies that are really red. So the blue ones are forming a lot of young stars, and so that's why they're blue. But then the red ones don't really have any star formation that's happening. And there's correlations of these colors with different properties like galaxies' stellar mass, for example. So galaxies like our own Milky Way, which I focused mostly on this talk, sit somewhere in the middle. They're kind of green if you had to put them on a blue-red color scale. But there's physical differences between these populations of galaxies. So these red galaxies tend to be more massive. They're more massive than the Milky Way, and they've basically completely shut off their star formation. And we don't really understand why, because when we look at this gas that's around them, there's a lot of cool gas that should fall onto the disk of the galaxy, get really dense, form stars, but they don't have star formation. They're completely red and dead is what we call them. So that's a very open question in astrophysics, is what stops star formation in these massive galaxies. And we think cosmic rays could also be important for that. But then there's dwarf galaxies. So we have dwarf galaxies in our local neighborhood, but there's also dwarf galaxies that are isolated. And so those tend to be very irregular in shape, and they have all sorts of, they're sort of blowing themselves apart in some cases. So they don't look as like disky and like spiral-like as what we see in these star-forming galaxies. So yeah, to answer your question, there's a lot of diversity in color and shape and like properties like mass and size, et cetera. So.
Yeah, to add on to that, at the dwarf galaxy scale in particular, there are some very weird looking galaxies, and trying to explain how those formed or what's going on in them it's right now one of the major challenges to the most widely accepted model for dark matter, lambda cold dark matter. But it also indirectly then poses a challenge to how well we understand the gastrophysics and star formation in the galaxy, because we can only observe the gas in the stars. You can never directly observe the dark matter. And so explaining, there are some galaxies that are just like they're like very spread out disks. And then there are some things that are just really compact. And our simulations actually they're not very successful at simulating either of those extremes. So that's been kind of an outstanding challenge. But there are ways to try to explain it that are more based on our interpretation of the observations, as opposed to taking the observations kind of at face value and saying, oh, our simulations match or they don't.
I wanted to ask a couple of the questions that were asked in our YouTube live stream from the audience there. One is, when gravitational waves hit a black hole or the gravitational well around a black hole, do they bounce back like hitting a wall, or does the wave continue through the black hole's space-time, potentially more in the time dimension or just through it, or what do you think?
I think I can answer this. It's I mean, you can in principle simulate this like any other wave. Gravitational waves can be almost lensed or refracted, like light through, a magnifying glass. If they sort of pass through a black hole, you can think of sort of that well as that lens. So there is. I don't know how much reflection would actually, or like bouncing back would happen. But they, in principle, theoretically, are certainly expected to sort of bend around the black hole, because you can sort of model them using a wave equation. You can consider them to be analogous to any other waves in the like electromagnetic spectrum, or pressure waves like we see in like earthquakes, for instance. There's a lot of, or sound waves. Yeah, so hopefully that answers the question a little bit.
So I was thinking about this a bit, and I think maybe a good way to visualize it might be like if you have a whirlpool in a riverbed or in the ocean. You have a big whirlpool, so it's dropped overall relative to the rest of the surface. That's kind of like the gravitational well of the black hole, or really any massive object, but certainly like a black hole. And then you have a kind of a surface wave that's coming along, and it runs into that. And part of it will go through it like a wave continues to go through it, but it'll be warped and as you say, potentially magnified or concentrated or refracted by the presence of this well, this whirlpool, in relative to the rest of the surface. I don't think that's a perfect analogy, but it gives some like insight to the nature of the problem. But I don't, as you say, I don't think there will be a lot of reflection, like hitting a wall, anything like that. So,
because typically, in order for that to happen, you would need some sort of a barrier, whereas this is just purely a well. Yeah, but it is an interesting question.
Yeah, it's an interesting thought experiment.
Some people write papers about it, but they're very complicated.
Yeah. You haven't asked yet. And then there's another question online. And then this gentleman here. We've got our work cut out for us tonight.
Great talk, Sam. You mentioned that you're not able to make measurements in part of the radio frequency, part of the spectrum. Is it known what you would see in that range, or is it kind of just a complete unknown? Do you have any speculation for what might be visible if we had telescopes that could look at that range?
Yeah. So again, going back to what we were discussing before, there's this whole electromagnetic spectrum of various different wavelengths of waves, everything from sub-micron scale, the sort of light that we can perceive with our eyes, to very, very even shorter wavelengths, the UV, the X-ray, the gamma rays, and so on and so forth. But then if you go longer wavelengths, you start getting into the realm of things that you can perceive with a radio telescope or a TV antenna, something like that. And it turns out, so kilohertz is, let's see, gigahertz is 21 centimeters is 2.5 gigahertz. So to get down to kilohertz, that's a factor of 1,000,000 times longer. 300 megahertz is a meter. Is another 1,000 times that. So kilometer scale. So once you get into a wavelength being a kilometer or longer, our atmosphere, our ionosphere, kind of the plasma in the upper atmosphere, is really effective at blocking and reflecting radiation from that. And so there are theoretical predictions for the sort of phenomena that we should see if we had an instrument that was capable of doing that outside of our own atmosphere. And I think one of the reasons that we want to, I mean, first of all, we want to build an instrument just to see what's there, right? To look at the sky in that particular wavelength. But I think one of the things that's predicted is, well, there's 21 centimeter cosmology. People should be able to see the hydrogen in the early universe at very, very far distances, even farther than the James Webb is capable of perceiving, before stars and galaxies have even formed. That's how far back and how far in distance. And so that can tell us a lot about the very early universe, like what the structure is and what's going on at that point. So that's, of course, very interesting because it can inform our understanding of the formation and evolution of the universe. In fact, we're going to have a talk at this lecture series sometime in the spring. We have a researcher, Ruby Byrne, who works on this topic, and she's agreed to give one of the lectures as part of this. So stay tuned. I haven't yet scheduled the date for her, but you'll hear a lot more about that. But in addition, aren't we expected to see exoplanets that are doing?
About that, I was going to talk about cosmic rays actually. But
oh, sure.
So the Earth.
He's a one-trick pony. This guy. He's all cosmic rays.
Yeah. So the Earth's atmosphere has a characteristic plasma frequency. So the ions that are in the Earth's atmosphere, they oscillate at a certain frequency that's around megahertz or tens of megahertz. So that's actually how AM radio works. Is we send out the radio signal at 1 to 10 megahertz. It bounces off the Earth's atmosphere, and that's why AM radio is always better signal than FM radio. But that also means we can't see anything beyond the Earth's atmosphere at below those frequencies. So one of the things that we have thought about is one of the direct measurements of cosmic rays could be this synchrotron radiation that they're emitting. So we have a lot of observations at gigahertz frequencies, but as these cosmic rays lose their energy due to radiating away their energy at these frequencies, they progressively go to lower and lower frequencies. And so we had been working with a team at JPL to try to make predictions for the signal that you would expect at megahertz frequencies from the halo of the Milky Way itself. So we would need for a constellation of satellites that would actually be able to measure things in the halo of our own galaxy that tell us about cosmic rays and magnetic fields. But that would be a potential interesting thing.
I also think the people on this panel can correct me if I'm wrong, but I think I've seen proposals to build like a radio telescope on the moon. Right. Yeah, to get around this. That's right. On the far side. Yep. The far, yeah.
Is that what it's called?
Yes.
Yeah.
So yes, of course. Following up on what Isabel was saying, there are proposals to build telescopes on the far side of the moon, because the benefit of being on the far side is you've got the big mass of the moon in between that antenna and the rest of the Earth. And even though, you think of light pollution, we can't see the dark sky very well from here in Los Angeles because of all the lights around. We get the same effect in the radio part of the spectrum because all of the electronic devices, our cell phones, our motors, all of these things are causing electromagnetic signals in the radio part of the spectrum, and they do the same sort of thing. They provide enough brightness from those signals that it swamps the signal from the deep sky objects. And so the benefit to building an instrument on the far side of the moon is that a lot of that light pollution in the radio part of the spectrum is blocked by the presence of the moon. And so yes, there's one instrument that's being proposed called FarSide, and it has a tortured acronym to make it work into FarSide, but there's the Lunar Crater Observatory. There's a number of different missions that are being proposed to build something there to do this sort of thing.
Yeah, it sounds like a really extreme idea, but it's actually very doable. Like there are, privately funded sort of spacecrafts that have landed on the moon to make radio observations that have sort of worked. The last one crashed, but it still got a measurement like right before it just like died. But yeah, what Cameron's talking about, the fact that we use radio waves as to communicate with each other is fantastic for us, but very annoying for radio astronomy. And this is why sort of radio telescopes that, if you kind of look up where radio telescopes are, they're very far away from civilization. Like we build ours here up 4 hours north in Owens Valley to get as far away as possible from sort of any sort of civilization. But yeah, by putting something on the far side of the moon, you can build it to be extraordinarily massive. It's really hard. But to get to those really long wavelengths, sort of like this is why car antennas look the way they do, because those wavelengths are quite long. And so they basically need to pass through the antenna and create an oscillation in sort of the voltage across the antenna that you can measure. And then eventually decode into sort of actual information like music. But putting something on the far side of the moon solves all of your problems.
So another question from our online audience. What is the interaction between dark matter and baryonic matter? Baryonic matter meaning normal matter, the matter, electrons and protons and the stuff that makes up us. Well, yeah, okay. What's the interaction between dark matter and normal matter, baryonic matter in the simulation with respect to inflow and outflow rates into the galaxy? I thought dark matter held the galaxies together. So what's the interaction? This is a good question for Isabel.
Yeah. So yeah, this is a good question. So the interaction that happens between dark matter and baryonic matter is in our simulations, or at least in most of our simulations, is only due to gravity. There is more dark matter, and it forms what's called a halo, like a giant, mostly spherical shape that then hosts the gas and the stars that form the galaxy. And it's the gravity that holds things in place, dark matter's gravity. There are, however, more exotic theories that propose what if there's some other interaction between the dark matter and the baryonic matter? This is pretty strongly constrained because if you had dark matter that was interacting with the baryons, you would expect to see something from it, and we don't. That's why the dark matter is dark. But still, I know of at least one group that has been trying to run these simulations where you have a very weak dark matter baryonic interaction, and it could actually affect the way that galaxies form in our simulations, or their simulations in this case.
Which group?
This was like Vera and Ethan.
Okay. We'll get to you again.
I hope you don't mind if I ask 5 questions at once. Oh, come on. Okay. Well, okay. Do you think Arecibo should be rebuilt?
Not really. I mean, it's really expensive. We have other telescopes that are very powerful. I think rebuilding Arecibo would have. I think there's a lot of funding problems for.
Just to make clear, so everyone's on the same page.
Sorry.
The Arecibo radio telescope was a radio telescope that was built in the 1960s and 70s in Puerto Rico. For a long time, it was the largest radio telescope, or the largest telescope in the world, because it's about 3 times the length of a football field across. And it sits in a natural bowl in the terrain, in the topography, in these karst valleys in Puerto Rico. So it was like held in this kind of spherical shape, and it operated for 50 or so years, but had some neglect in the last 10 or so years, and eventually just kind of collapsed under its own weight about 5 or so years ago. I think during COVID, it collapsed. And so, yeah, there's been talk about reconstructing something, but the point is, it's a zero-sum game in terms of the funding that goes towards these sorts of things. And so is there better science that could be done with a different type of instrument than that? It was right for its own time. There is another instrument like that called the FAST telescope that's built in Tibet, on the Tibetan plateau in China. That's about 3 times the size of the Arecibo radio telescope and has done some great science, but yeah, there's only so much funding that can go towards these things, and it's unclear if that's the best use of the funding at the time. Do you guys want to add anything? Sounds like he has like 4 more questions. So, all right.
Great questions. So I'm very privileged to be here, which I almost expect that Dr. Richard Feynman lectured in this room once. Oh, this wasn't built. Okay, across the street. Okay, but along his lines, one of his most famous observations is that the fine structure constant 1/137 is found all over the place in physics, whether on a micro level or on a macro level in terms of the galaxies. So that's another perfect example of a fractal thing, right? So is there any further, well, he even called it magical. So is there any further development along these lines of, do you find this, the 137 somewhere in all these simulations? And also, is there any mention of the number 15, the luckiest number in the world?
15. In terms of fine structure, the main way in which I think of finding it is in fine structure lines, emission and absorption lines that we find in the quantum nature of the atoms that are in the simulation, but we have to program that in effectively. That doesn't just arise and emerge out of the results of this kind of gravitational hydrodynamic simulation. You don't see the results of this. But when you incorporate the quantum nature of the constituents of those simulations and encounter that there will be radiation that comes out that are fine structure lines, but it's kind of forced in there because we know that's what's behaving below the resolution elements of the simulation. In terms of 15, why is 15 the luckiest number in the
I have not.
No, I don't think so.
No.
Sorry.
It's okay. 137 is still there somewhere.
It's there somewhere. So do you have like 3 other questions? Oh boy. Okay.
All right. So since this is a I'm here to supply simulating questions in case nobody. Okay, he has one. Okay, then.
Okay. We'll come back to you. We'll come back to you.
Hi. So in some of those simulations, there was that number z, and as that got closer towards 0, the simulation started speeding up. So could you explain why that happens?
Excellent.
Yeah.
Excellent.
So Z is redshift. So that's basically how we measure. As the universe expands, it stretches light, and so things that are reddened more are further away on these large time scales or large distance scales. So yeah, the universe's expansion isn't linear with time. So redshift, the amount that the universe expanded at a given interval of time was actually faster earlier in the universe. So the Nobel Prize discovery in 2011 was that the universe is expanding at an accelerating rate, but the acceleration is actually negative. So the universe's acceleration is, and that's because of a formalism of how it's defined in the equations. It's a negative. There's a negative sign. So the universe was expanding faster earlier in time, closer to the Big Bang than it is today, and so that's how you get the fact that the redshift and time are spaced that way.
So yeah, we use redshift as in a variety of ways in astrophysics, but the way in which it was represented in the simulation is as a function of time. So at very high redshift, that's essentially when the time is closer to the Big Bang. So T equals 0 at Z being redshift equals like infinity. That's the initial conditions for the simulation. And then it runs forward to T equals 13.8 billion years, giga years, which is today. And that's when Z equals 0, when redshift equals 0. So essentially you go from, at the early part of that simulation, the redshift is 100 and then 10 and then 5 and then 1 and then 0.5 all the way down to present day, and it becomes 0. And that's the equivalent of time being at the Big Bang and then being all the way to 13.8 billion years later, which is right now. But it's super confusing, and there's not just like an equation that I can write down that governs that. There are cosmology calculators that you can find online that will do that conversion for you if you assume certain cosmological parameters, like what the flatness, you know, the geometry of the universe is, and what the amount of matter relative to the critical density rate. There's a bunch of different cosmological parameters, which we kind of know what they are from various different telescopes, but we don't entirely know what they all are, but we're getting to a better point as time moves on to be able to constrain those. And then you can get a perfect kind of one-to-one correlation between time and redshift.
Something else I just wanted to note is in some of our simulations, we have, what we call snapshots, where we read out all of the data at like kind of set times. And in a lot of our simulations, we have more snapshots that happen at later times, just because we're more interested in what happens at later times based on maybe some observation or, I mean, as you saw, like one of those simulations, like that's kind of when the Milky Way like started to look like the Milky Way. So if you just want to look at your simulation when it looks like the Milky Way, you want more snapshots then.
Any other questions?
Hi. So my question is, what exactly about the accretion disk, like when planets, like for instance, like the Earth rotates, why is it like, what chooses like the axis of it? Like, is it the magnetic field that it creates it, like instead of rotating like oriented this way or that way? Like, what chooses the top and the bottom of the spin of the galaxies?
Of the galaxies or of the planets in the solar system, or both? Of the galaxies. Why do they have the orientation of the disk? Why do they rotate in a particular direction and not another different direction here?
Yeah, so we see some we see basically a uniform distribution of the orientation of galaxies on the sky, but the direction in which they're rotating is set by like the conservation of angular momentum. So the history of the galaxy's mergers will play a role. So like if you had a galaxy that's colliding like basically dead on versus a galaxy that collided with it that was very massive at an angle, that will set basically what direction that vector or that direction is of the rotation axis. And so like when we at different galaxies, like we see some that are edge on and we see some that are like directly face on, but that distribution is essentially uniform because, as you could imagine, like different galaxies have been scrambled by different merger histories. And so that basically takes out any preferential direction. But there are some areas of research that are trying to figure out if you look at galaxies that are maybe aligned with some dark matter filament or something, whether the preferential accretion of gas into those little halos of dark matter from the larger scale filament might set a preferential direction. I think this is a field of study of intrinsic alignment of galaxies and how that connects to large scale structure. I don't know as much about it. It is an area of research.
But just to further provide like an illustration of what Sam was saying, if this is the disk of your galaxy, this cheap notepad that I just found over here. So this is our edge on galaxy, right? And it's rotating like in this direction. So its vectors going up like that. And then another galaxy comes flying in from this direction and slams into it. Because of conservation of momentum, now the disk might be offset because all this stuff came in and transferred its rotation and its angular momentum to that system. And so now it'll be offset. But then maybe one comes in from this direction and resets it. So it's really a dynamic setup that you might see a galaxy that's aligned like this right now, but in another billion years, it might be offset or like that because of the interactions that it has with its neighbors. It can.
It depends on how strong the fields are. So there's another group that's looking into how magnetic fields can potentially shape galaxies and their structure. Their simulations find magnetic fields that are a lot stronger than what we find in our simulations, and that has some physical reasons and it has some numerical reasons. Just have to do with how they implement the physics in their code versus ours. I'm of the opinion that I don't think the magnetic fields are strong enough to actually shape the structure of the galaxy, but it is possible. I mean, on larger or on smaller scales, like in star forming regions, magnetic fields can be very strong. Because as the gas collapses into these really dense pockets, the magnetic fields basically get pushed together, and so they're stronger. And so that can basically back react on the gas, and then the gas starts to flow along the field lines if they're very ordered, and that can influence how these clouds evolve and form. That same principle could apply to galaxies, but at least the answer isn't out yet. It depends on what the actual field strengths are, and that's very active area of research in both theory and observations because, as I sort of noted, it's hard to measure the field strengths and geometries directly, and they're sensitive to all these assumptions. But if the magnetic fields were strong enough, some simulations have found that it can shape basically it can influence how gas gets inflowed into the galaxy, which would then shape how the rotation axis is directed.
I think this may be our final question as we've reached the end of the evening. That's okay. Just one, not five.
So this is what you do, Cameron, right? This is the modeling thing. This is your expertise. Yeah. That's nice. So dark matter, what is that? Is there just the unknown about how that's shaping? Also, could that have anything to do with the spin, or does that contradict that it doesn't interact? Or of the spins of the galaxies and the shapes of the galaxies, how does dark matter affect that? Or, because I'm confused because it's not supposed to interact, but it does.
Yeah. Okay. So when I say that dark matter doesn't interact, I mean, it doesn't interact electromagnetically. It doesn't give off light. It could have other interactions. We know it has gravitational interactions. And it's the gravity that ultimately determines the spin of the galaxy. In fact, actually, it was the spin of the gas in galaxies that provided the original evidence for dark matter. Vera Rubin, who was an astrophysicist back in the 1970s, noticed that the gas in stars in the outer parts of galaxies was rotating faster than you would expect it to if you estimated the mass of the galaxy just based on the visible starlight. This missing mass problem is now what we call dark matter. So yeah, part of this, in some of my earlier answers, I may have just said dark matter doesn't interact as sort of a shorthand. I mean that, but we know that dark matter interacts with gravity. We have other evidence as well, like the gravitational lensing of galaxies and stars. If you have like a giant clump of dark matter in the way, it bends light from other objects behind it. And it creates like these kind of cool quadruple images. You can look this up. It's very cool.
But yeah, the dark matter for the most part, just to add on what Isabel stated there, the dark matter for the most part is like this unseen scaffolding on which the stuff that we can see exists. The dark matter makes up the bulk of the mass and the material. We just can't see it directly, but it influences the behavior of the stuff that we can see. And so we can kind of infer the presence of it because it draws things in gravitationally to the same regions. And can affect the rotation, can affect the dynamics of the system. But it, as Bill said, it doesn't interact electromagnetically. We can't physically see it. We just can infer its presence indirectly based on the behavior of the stuff that we can see. And Sam's model here. So this is from the center of a the center of a galaxy, and this is the radius, the distance away from the center of the galaxy. And this is, oh my goodness. And this is the velocity at which that stuff is rotating around the galaxy. So in the core of the galaxy, it's not moving very quickly, but as you go farther out, it's rotating more quickly. And then it plateaus at a certain level, which implies there's a lot of dark matter that's there. There's a lot of unseen mass that's in the outskirts of this galaxy. We just can't see it.
Dark matter outnumbers visible matter by a 5-to-1 ratio. In terms of mass.
Okay, it is now 10 o'clock. I am tired. You're probably tired as well. Thank you guys for sticking around. Thanks to our speaker and our panelists. We will be back. We will be back next month. Stay tuned. Check out your online our advertisements on Facebook and Instagram and Twitter and so on and so forth. And if you're interested, Astronomy on Tap is a week from Monday night, all about the Chandra X-ray telescope, Monday the 16th at the in Old Town Pasadena. It should be great. Thanks for joining us. We'll see you guys next month.